Hello learners, welcome to Education Online. I'm teacher Willa Lucia. So today we shall be looking at characteristics of body under action of couple. So we have it as our characteristics. Characteristics of bodies under the action of couple. So in our previous lesson we say that a couple refers to two equal but parallel forces whose lines of action do not meet. So if there are two unparalleled forces, like we say here, we have these are already two opposite parallel forces. We shall say this is F1 and this is our force 2. We can see that their line of action do not actually meet. This one is acting at one end of our rod there, and then this one is acting at this end. So what are the characteristics of such bodies under the action of couple? So we shall say that the first characteristic could be the resultant force. Their resultant force should be equals to 0. Equal to 0. So if their resultant is equals to 0, how would their resultant, how does this come about? We already say that for this force here to balance up with that force, and for you to get a couple, that means that your force, this force F1 here, should be equals to F2. You need your force, your F1 should be equal to force F2. That means that if you have applied a force of 3 Newton here, to balance this force, you will need another force of 3 Newton as F2. So this one will help you balance that. How would you get the resultant as 0? Let's look at this. We say our force F1 is there and this is our F2. We are assuming that so this is our rod. Let's assume that this is the body that couple is going to act upon. So this is it, and here we are saying that this one is, since we say this one should be F1 and then this is our F2, and we are saying that our F1 should be the F1, the first force you apply, should be equal to our second force. That means that if we have here let me say 5, we have a weight here of 5 kilogram, and then we have another weight here of 5 kilogram. So we are having these two weights the same in order to balance that. Then how do you get the force? Here is the weight. This is not the force, because we say that to get weight, our force is equals to weight of the body. And what does the weight of the body equals to? The weight of the body will be equal to the mass of the body times the acceleration of the body, acceleration due due to gravity. Why are we having it like that? Because we know that for any body that is falling freely, there is a gravitational pull that acts on the body. So for this case, for you to get the weight of the body, you will have to get the mass and then multiply it by the acceleration due to gravity. So that means that in that case, we shall have our force as, since we said that the force is equal to the weight of the body, and we say the weight of the body is the equivalent to the mass of the body and acceleration due to gravity, we shall have our force as the mass, which is, we have it as our 5 kilogram times the acceleration due to gravity. In this case, we are taking it as 10. So we shall have our force, which is equals to 5 times 10. We shall have force is equals to 50 Newton. That means that the force we are applying here will give us, if this is mass of 5 kilogram, and then this is again mass of 5 kilogram, to balance it, that means that the two forces here will be, the first one here will be 50 Newton, and the force that will be acting here to balance that force is 50 Newton. We want to find the resultant of this force. Since we are saying that for any body, as far as our characteristic of a body under the action of a couple, the resultant force should be 0. How would you get the resultant? You see that our force here is moving in the opposite direction from this other force here. This one is going downwards, whereas this one is going upwards. That means to get the resultant, when you want to get the resultant, you get it will be equals to upward force, the upward forces, minus downward forces. When we are talking about the upward forces and the downward forces, we are meaning those ones that are pointing in the upper direction, and the downward one is this one pointing in the lower direction. So we shall have our upward force is only this. So we shall have it as 50 Newton, which is subtracting the forces that are acting in the downward direction. We have it as 50. So what would be our resultant there? Our force is going to be here. This one is going to be 0. You see? That means that our resultant, the forces acting on this is equivalent to 0 if you get their resultant. Because we are saying that a resultant force is just a single force that when you apply on the body will give you the same effect as those forces you already had applied. So we are just converting these two forces into a single force. That means that when you convert this and you subtract these ones, you'll get 0, giving us the first reason as to why we have this characteristic there. So let us look at another characteristic of a body under the action of a couple. We are saying that the turning effects of the force should cause rotation. So let's have it here. Turning effect of the force should cause rotation, meaning that for a body to undergo this couple here, it has to be rotating. That means that the force you are applying on the body should be in position to make this body rotate, to twist the body. So that means, let's look at this again. Okay, we have this here. If I apply a force on this, this is tissue paper, so I want to apply downward force on this. We say that the body has to rotate as you apply the force on it. So let's see whether it can actually rotate. So this is our tissue paper, and this is the force I'm applying at this end here. You see that when I try pulling it, what happens? It keeps on rotating. Have you seen that? So that means that all the forces you are going to apply on the object should cause rotation on the object. What is another characteristic of these bodies that are under the action of couple? We are saying that the bodies should be, the forces should be acting in opposite direction. So this is the third one. Should be acting in opposite direction. Okay. That means that if you want the bodies to balance or to come to stop, as I'm rotating this, if I'm to be rotating it at a very high speed, okay, there is a lot of friction in this, which doesn't allow it to move faster. And it is like it tears easily. So I wanted to try to rotate this. So if it is at a higher speed, for me to balance this, when I leave it and it continues rotating, for me to balance this, I will not have to add another force this way. I will not say that I'm going to pull it right here to allow it balance or to stop. That means I will have to apply the force in the other opposite direction, taking it in another direction, upwards. Or, okay, let's look at it on the chalkboard. We have this. That is where we are applying the force. There. So as you're pulling this, let's first take this one. When you pull this, it will keep on rotating this meter rule here, or whatever this object is. So as it is rotating it here, I think this one would do better. As I pull this and I'm rotating it here, it keeps on rotating alone. If I want to stop it or balance it, that means I need to apply another force this way so that it can balance each other, or it can come to a stop. So that means that I need I need forces, two or more, but acting in opposite direction. So when they're acting in opposite direction, that means that that body there is already acting under the action of a couple. So those are the major three characteristics of a body under the action of a couple. So let us look at the moment of a couple. Let us have our moment of a couple here. So, moment of a couple. How would you find the moment of a couple? We are saying that a moment of a couple is equal to the product of one force and then the perpendicular distance between the forces acting. So how is this? Let's take a look at this. We are having, let's take something circular like that. Or we first write some definition here. Moment of a couple. A couple is the product of one of the forces acting on a body and the perpendicular distance. We have it here as the perpendicular distance, distance between the two forces. So if it is like that, if we are saying it's the product of one of the forces and the perpendicular distance between them, why are we taking it as one force? Because we say that for a couple, for a body to be under the action of couple, we need the two forces to be acting in opposite direction. They are parallel to each other, but they should be equal. That means when you apply a force of 30 Newton in one direction, in the other direction you need another force to balance that force, and the force should be equivalent to the same. That means you need another 30 Newton to balance the first force you applied. So how will it look like? Let's have a look at this. If we have there, so we have this, we have a force here we've applied. Let's say it is our F1. And then we have another force, we need to balance it as F2. So this is the distance. Look at the distance between this force and that. Let's have it here, up to down, as our D. We are taking the moment to be one force because we say this force here is equals to that force. That means our F1 is equals to our F2. They are the same. So to get the moment of a force, moment of a couple, will be equals to, I think we should write it this way, a moment of couple will be equals to one of these forces. We shall have one force times their distance, the perpendicular distance between. Perpendicular distance. So you can choose. You can either choose F2 or you can choose F1. There is no problem with that because we are saying those two are equal but opposite. So we shall have our moment of a couple as let's take our F1. If we take F1 as the force we are considering, there should be times the perpendicular distance between those two forces. So what is our perpendicular distance here? You'll see that our F1 is acting right up here, and then we have our F2 acting just right below here. So the distance between this point of application of F2 from this is what we are considering. And in this case, we have it as our D. This D means here the diameter of the circle. So we are taking it as our D, which will give us our moment of couple will be F1D. That is if they have given you the diameter. What if they have not given you the diameter, but instead they have given you the radius of the circle? What do you do? So let's see if it is the radius. What shall we do with that? So if we have it as radius, we know that to get diameter, you need to add this diameter here is equivalent to 2 radii here. So you need 2 radii to to get a diameter. Let's see this. If we have this is still our circle there, we have this force here, our F1, and then we have this one here as our F2. So to move from there up to here, okay. To move from there up to here, we are saying that this one is the diameter, but we said this one here can be radius 1 and radius 2. Because if you divide it in the middle, this diameter, when you divide it in the middle, that's when you get the distance known as the radius. From this point here up to the center will give you the radius. So that means to get diameter is equals to R1 plus R2, because you see this one comes from here up to ends in the center. Then this one moves from this one and goes up to the end. So when they have given you instead the radius instead of the diameter, what do? You can get it as your moment of a force will be equals to, we can have your F1 times the radius, which is R2 here, plus your F2 times your your radius R1. So that means that the moment of a force, when they have given you the radius, you can as well multiply it just with that, because here now we are taking this one as our fixed point, the center. That means you need to multiply this force here and the distance up to the center. Then you can multiply the next one up to this distance. We have not taken only one. We have not taken only one force, because it is not the total distance between the two forces, but this distance instead this time ends in the center, doesn't reach up to the point of application of the other force. So we shall have it as our R1 R2 plus F2 R1. That is in case they have given you the radius instead of the diameter. So what do you think could be the conditions for a rigid body to be in equilibrium? We've been saying that for this, when a body is balancing, that means that the body is in equilibrium. So what are those conditions? We take it there. Conditions for body to be in equilibrium. So what could be the possible conditions for a body to balance? Like I have this, I want it to balance on this, and I'm going to be applying several forces on that. What could be the possible reason? What could be that thing that can make it balance? Because I might be applying my forces everywhere and anyhow, and it fails to balance. But it can also balance by coincidence. You see, you are just applying it anyhow, but then that means that there is a factor there you also considered without knowing for it to balance. So these conditions can be, the first condition, we can have it as the sum of upward forces should be equal to the sum of the downward forces. So that means that when you apply force on an object, a rigid body, let's take it there. We are applying some forces on that. We take this as our rigid body here. We want this body to balance. How can we make this body to balance? Yet we are applying force on it Because if we put force here, that means that if we have our F1 here, we do not have force here, it's not going to balance. It will fall. So that means that the body is not in equilibrium. What if we apply another force here? Look at these forces. We have several forces. Here, we have upwards and then downwards. So our condition will be that all this force you are applying here, 3, we shall have this as our 4 and 5. If you sum up this force that is acting in the upward direction, should be equal to the forces you've applied in the downer direction. Because if they do not balance out, that means that their resultant is not 0. So that means this body won't be in equilibrium. So first condition is all these forces up should be equal to the total forces downwards. So what could be another condition there? Let's look. Since we say we have to balance it by balancing all the force upwards and the downwards, so we can also have it as the clockwise moment. All the clockwise moment should be equal to the sum of the anticlockwise moment there. The sum of clockwise moment should be equal to anticlockwise moment. So how would you find that? That means that you will need to find which forces are acting in the clockwise direction and which forces are acting in the anti-clockwise direction. So when you find those two, then you try to compare. So for you to have an equilibrium, that means that the two acting, the clockwise moment and the anti-clockwise moment, should be equal. That is how a body will be in equilibrium. So I am going to show you how we shall find those forces in the anti-clockwise direction in order for us to find the moment, the clockwise moment, and also in order to find the anti-clockwise moment. Let's find that in this example here. So in our example, we have a rigid body here. So we have this body. So in our rigid body, we have some forces acting on it, but we have this body. Our body is on a knife edge, or we can have it as the pivot. We have a force acting in this direction, which is has not been given here. It is just F. We have it as our F Newton. So we have another force acting downwards here, which is, this one is a mass. They hang the mass here of 30 kilogram. So this mass is 40 centimeters away from the pivot. So we have another mass being here, which is of 4 kilogram. And the distance between that mass applied is 20 centimeters. So what do we have here? We have this, the whole of this, up to this point of application of the force, as this distance here has been given to us as 100 centimeters. So they are telling us to find force F. So this is our example. How do we find this force F here? Let's take a look at this right here. So for us to find force F, we need to know in what direction is these things are the forces acting. Are they in the clockwise direction or they are in the anti-clockwise direction? So how would you know that? Let's look at let's look at our F, because we say that to find moment we need that from the principle of moment. We are saying that anti-clockwise moment, we can start with the clockwise moment is equals to anti-clockwise moment. So in this case, which ones are the clockwise? Which one is in the clockwise moment and which one is in the anti-clockwise moment? Let's take a look at this. When we pull this force upwards, in which direction is it going to make this rod here, the body, rotate? So when you're pulling it up, you will see that this one here will start rotating in this direction because the force is going to be forcing this upwards, this end here. So this one will cause rotation in the anti-clockwise direction. That means that our force F1 is acting in the anti-clockwise direction. So this one is anti-clockwise. Let's come to this one. What happens if you pull this downwards? When you're pulling this down, you will see that this end here is going to rotate in this direction here, meaning that this forces, when you apply it, it will cause rotation in the clockwise direction. So this one here will go in the clockwise. This is clockwise direction. What of this one? When we pull this down, what happens to this end? This end is going to be falling this side, so it will be rotating in the anti-clockwise direction. Then here we're having anti-clockwise. So if you have that, then you will know what to write there. You'll see that our clockwise moment has only this, and this is not force, this is the mass. But to get the force, you can, if you have the mass, you can get the force, because the force is the same as the weight. So here our force will be 4 times acceleration due to gravity. In this case we are taking it as 10, so we shall have it as 4 times 10, and we are saying that it is going to be let us have it here as our force times the perpendicular distance. Even here it is force times distance. So our force in the clockwise direction, we only have this, which is the mass. We shall have it as 4 times 10 to give us the force, times what is the distance of this force here, this mass from the pivot. You can see that from here you move up to 20 centimeters, meaning that our mass here has been hung in the 20 centimeters mark. So we shall have it as 20. Remember, it is in centimeters. You change it into meters, which is 100, which is equivalent to, you come to that side in the anti-clockwise, we have this force and we have this one. So this force here, we have it as our F, is what we want to find. What is the distance of this force from this pivot? We don't know, but we have the whole distance up to there. So we shall get this distance from here up to there. You subtract this one out, because we want from only here up to there, giving us, it's going to be times, our distance is going to be 100 minus this 40 here, to give us from here, from this pivot up to there. We are taking that one out. So this one minus 40, the whole of this is over 100. But this time we still have this force is acting parallel to this one. So this one, since they are all anti-clockwise, we are going to subtract. This one is in a different direction and the other one is in a different direction. We shall have it as minus our 30 times 10. Then this one is going to be multiplied by the distance of this 30 from the pivot, which is 40 centimeters, 40 out of 100. So we shall have it here as, this will give us 40 times, this one when you cancel with that, you'll have 0.2 is equals to our F. This one when you subtract that, you will get, this one will be 60 divided by 100 minus, this will be 300 times 0.4. So we shall have this as, this one multiplied by this will give you 8 is equals to this one and that, this one will cancel with that. We shall have 0.6F minus 300 times that. What shall we have? We shall have around 112. So now this time, how would you eliminate that? You're going to take this, that side we are making our F as the subject. So we shall have it as 8 plus 112 is equals to 0.6 F. So divide through by 0.6 and divide through by 0.6. That means that here we shall have it as, that is going to give us 120. Divide by 0.6 and divide is equals to, this time we are dividing that. That means this one will cancel out. We shall have our F. So what would be our F here? Our F will be around, this is going to give us like 100 and, around 118, 116. That is going to give us 116. Let's do some math here. That is going to, that is times that. 1.8. This is going to give us 0.6. This gives us 100 and that Newton. 100 and, okay, this one is this side. Is 168, which you can also, that is 0.6. You can round it off as well. So if you have that, now we have seen how we can use how we can find the clockwise moment and the anti-clockwise moment. We've known about the characteristics of bodies and the action of couple. So with that, we've come to the end of our lesson for today. We shall meet again in our next lesson. Bye.